If we're looking at exponential functions are going to be functions where the variable is in the exponent. So if we look over here off to the right, we've got our basic form of an exponential function, y equals a to the x power. You can see this exponent up here this variable is in the exponent. That's what makes it an exponential function. Couple examples of exponential functions. We've got y equals 2 to the x, we've got y equals 3 to the x power, and then we have y equals 0.25 to the x power. You can notice for my 2 to the x power and my 3 to the x power, which are numbers that are greater than 1, I can see that I've got an increase here, or I have exponential growth. From left to right, the y value is increasing. Now, on the flip side, if we look at y equals 0.25 to the x power, which is a number that is less than 1, we can see this is where we have our exponential decay. Because those numbers, those y values are getting smaller as we increase from left to right. Another thing we can notice here, just a small little difference between these two, 2 to the x power and 3 to the x power. Obviously 3 to the x power is going to increase at a faster rate than 2 to the x power, and that's simply because this base of 3 is larger than the base of 2. So it's going to continue to increase at a much faster rate. Last thing we want to look at is what we call an asymptote. Because our exponential functions will continue to approach values, but never actually equal that value. So if we look here at my y equals 2 to the x and y equals 3 to the x, if you look at this left-hand side of the functions, this left-hand side is going to continue to flatten out, and it's going to get closer and closer and closer and closer to y equals 0, which is the x-axis, but it's never actually going to touch it. That is an asymptote, something that it approaches and it gets closer and closer and closer and closer to, but it never actually touches. You can see that on this side as well. We can see this function is going to continue to kind of flatten out and keep on working down here, but it will never actually cross that x-axis. It's approaching the asymptote, so it's approaching the value of y equals 0, but it's never actually going to be y equals 0. A couple examples we have about exponential growth. Typical places where we're going to see it. Obviously, we've got a quantity that's getting larger, and then the key here is how fast it is growing. Linear functions, they grow at the same rate. Exponential functions, as they start to grow, they take off. People talk about things increasing exponentially. That's what we're talking about. We're talking about something where it's growing at a high rate. So if we have some sort of investments with a fixed interest rate, so if you invest money at a bank and they give you an interest rate, that is going to be an exponential growth. Over time, you're going to see it's going to start to grow more. In biology, we could see, or science, we could see microorganisms in a culture dish. Those are going to kind of grow from each other. Each organism doubles, and then each organism that now is created doubles, so we're going to have an exponential relationship. And then the last thing we'll see is population size. Most populations have some sort of exponential function. Typically, it is growth. On the flip side of that, we've got exponential decay, which is exactly what you would think. Things are becoming smaller, and then it decays much slowly. So at the beginning, it decreases very quickly, and then as it is, as your x value, normally time is increasing, your y value just gets smaller and smaller and smaller, but at a slower rate. Examples of this would be rate at which an object cools. So if we took hot water, we put it in a freezer, we would see that it would decrease very quickly at first, and then that temperature would kind of start to kind of plateau as we approach freezing, or whatever the temperature of the freezer was. The number of atoms in a radioactive isotope is also going to continue to decrease at this same relationship, and then actually probably the thing that we can relate to the most would be the value of a car as it depreciates. Now that's only up to a certain point, because we know as cars get older, they lose value, and then once they get to a certain point, that value actually starts to increase again. So we're only talking about those values while they're decreasing. A big equation we're going to want to know, understand how to use, and understand what's going on is our exponential growth and decay equation. The good thing is it's the same equation for both. We've got our final amount, which is our A of t, which is in purple here. It is equal to our initial amount, which is in green, times 1. So there's always going to be our constant of 1 in here. And then we have this plus or minus the rate of increase, and then we have that 1 plus or minus rate of increase being raised to the t power. This plus or minus is very important. This plus or minus tells you the difference between exponential growth and exponential decay. If I say that something is increasing at a 5% rate of increase, we're going to use a plus sign, so it'll be 1 plus 0.05, because that's what 5% is. If I said that something was decreasing at a 25% rate, then I would do 1 minus 0.25. So that's why we have our plus or minus here, because depending on the problem, we're going to use the same exact equation. We just have to decide, is it growth or is it decay? Alright, so we've got the initial value times 1 plus or minus the rate raised to whatever our variable is, t, x, whatever it is. So let's try and build one together, and then we'll look at what the graph looks like. We've got an example here. Tony purchased a 1959 Gibson Les Paul guitar in 2000 for $12,000. It's been estimated that the value increases by 14% each year. Use the graph to evaluate, and we will evaluate that. When will the guitar be $60,000? So if we want to do some forward thinking here, we can try and predict when it's going to be $60,000. We've got to create our equation first, though. Remember we said, and I'll just call it y for now, the value after whatever amount of time, actually we'll call it a of x is what we'll call it. And we know this a of x would be, when is it $60,000? We've got to take our initial value, multiply it by 1. Since this is an increase problem, we've got a growth, so it'll be 1 plus. Our rate is 14%, and then it's raised to the x power. So if we want to write this down in here, we'll say that a of x is equal to our initial value, which is 12,000. So I'm going to plug in 12,000 for A. And I've got inside of parentheses, I have 1 plus my rate. My rate is 14%. Remember, 14% is equal to 0.14. To turn a percentage into a number that we can work with, we move the decimal 2 spots to the left. So if I had 14%, I move my decimal 1, 2, put it here, and that gives me 0.14, which is what I plugged in right here. And for right now, since we're just doing it in general, we'll throw an x in there. So this is what our function would look like. It would be a of x is equal to 12,000 and then I've got 1.14 because I have a 14% increase, and my exponent, or I'm sorry, my variable goes up in my exponent. Now, we're trying to figure out when it's worth $60,000. The best way to do this for us right now is to just graph it. So I already have it graphed. If we look at a snapshot of what this graph looks like in Desmos, we can see here is my y-axis. And I've got my labels for my y-axis over here, 20,000, 30,000, 40,000, 50,000, 60,000. What I did is I created in red is the function that we're looking at. So the function that we built, let me get that back in the picture here. This function that we built is in the red. Okay, so this is being represented by this red line here. And then all I did was put a blue line in that represents $60,000. So what we're looking for is this point where these two cross. So I can see it's going to be worth $60,000 because the Y value is how much it's worth after 12.28 years. So I could say, 12.3 years. It's going to be worth $60,000. Just to be safe, we can round that up and say after 13 years, that guitar is going to be worth $60,000, which we can see that is increasing at an exponential rate. This snapshot, we can see it's got a little bend to it, and it's increasing very quickly. One more example we'll look at. So we're talking about a value of a truck. If we bought a new truck for $28,000 and it's decreasing by 9.5% each year, our exponential function obviously here is going to be decay. So we're going to come up with the function, and then we'll look at the graph to find out when that truck is worth $5,000. So to write our function again, we've got our a to the x is equal to our initial value times 1, and we said this is a decrease problem, so we should put a minus sign. 9.5%, I write it as 0.095, and I put my exponent in here. Okay, so if I want the entire function here, I would say I have a to the x equals initial value is 28,000, so I got 28,000 times 1 minus 0.0095 would give me 0.905, and I got that whole thing being raised to my exponent here. So all I needed was my initial value, and I've got my 1 minus my rate, and that gives me my exponential decay function. If we want to find when this truck's worth $5,000, we can look at the graph. Again, the red would be our function. We can see it's decreasing here at an exponential rate. We've got a little bit of a bend to our function here. In blue, all I did was put y equals 5,000, so I got my $5,000 line here. Once they cross, that tells me exactly how long it's going to be until this is worth $5,000, and I can see the answer here would be 17.259. Let's peek back up at the question to see what we're looking at. We're looking at in terms of years. So we got 17.259 years, which we'll call 18. So after 18 years, we can see that value is going to be $5,000. This is just a quick review of our exponential functions and then our exponential growth and decay equation and how to use it.